So here on we start with questions for ionic equilibrium, and the question being number 11, and the first one for ionic equilibrium, it goes like this. Predict the direction of the reaction HNO2 aqueous plus Cn minus aqueous in equilibrium with HCN aqueous plus NO2 minus aqueous, and given the acid dissociation constants are Ka for HNO2 is 4.5 into 10 to the power minus 4 and Ka for HCN is equal to 4.9 into 10 to the power minus 10. So as you see, there is a difference in the powers of 10 for both the Kas. So how will we do this question?
Yeah, see, basically the stronger the acid dissociation constant of an acid, the stronger is the acid, right?
Right.
So Ka for HNO2, since it is much greater than Ka for HCN, we know that HNO2 is a stronger acid.
That's right.
Right. Than HCN. Now, in a reaction, let's see what is the reaction given to us. Cn minus aqueous. Yeah. So in this reaction, when two acids are competing for releasing proton, the stronger acid obviously wins.
That's right.
So here, since HNO2 is a stronger acid than HCN, and we know that acids release proton or H plus in an aqueous solution, then we see that here HNO2, if we move from left to right, then HNO2 is releasing H plus.
That's right.
Right? That means it's behaving like an acid. And since HNO2 is a stronger acid, even in the presence of HCN, it will behave like an acid.
Right.
It will release its H plus. So the reaction will move from left to right.
That's right. So basically the concept here important being that we need to first compare the Kas for both the acids and see the one being stronger, and that is how the reaction will proceed. So this was an easy question, the first one for ionic equilibrium. Now we proceed on to the next one. So here comes question number 12, that is, acetic acid of concentration 0.1 molar is taken. The acid dissociation constant, that is Ka, is 1.74 into 10 to the power minus 5, and we are to find number 1, the concentrations of H plus and CH3COO minus ion, and secondly the CH3COO minus ion concentration if 0.1 molar of HCl is added to the solution. So how will we do this question?
Yeah, okay. So we are given the that we have an aqueous solution of acetic acid. So this is how the acid dissociation will take place. It's an acid, so it will form hydronium ions in aqueous solution, right? Let's say we start with 1 mole of this, right? And let's say the degree of dissociation is alpha. So
That's
alpha
right.
moles of CH3COH will be dissociated, and since the stoichiometric coefficients are 1, alpha moles each of these ions will be formed. Now we know that the acid dissociation constant is 1.74 into 10 raised to the power minus 5.
Right.
And yeah, so in the first part I need to find out the concentrations of H plus and CH3COO minus ions. Here we will use CH3COOH is a weak acid, so I can use Oswald's dilution law.
Exactly.
According to Oswald's dilution law, the hydronium ion concentration will be equal to under root of Ka into C.
Yes,
and I know both these values, they are given to me in the question. Yeah. So I'll substitute the values 1.74 into 10 raised to the power minus 5 into 0.1, which is 1.32 into 10 raised to the power minus 3.
That's right.
If instead of remembering the formula, if you want to derive it, you can do that. Ka will be the concentrations of CH3COO minus and H plus upon CH3COOH. So this will be alpha square upon 1 minus alpha. So, and 1 minus alpha will approximately be equal to 1. So
As
this will
alpha is
approximately be
very
alpha
small.
square. Yeah, basically C alpha square, because we in general we start with the concentration C.
Yeah.
So it will be C alpha square. So yeah. So yeah, we found out the concentrations of H3O plus, and which will also be equal to the concentration of CH3COO minus, since the stoichiometric coefficients are same.
Exactly.
So it is 1.32 into 10 raised power minus 3 molar. Okay. Now we move on to part B. What happens to this solution? What happens to the hydronium ion concentration if I add 0.1 molar HCl to 0.1 molar CH3COOH
minus?
Okay, let's see what will happen. See, this is the reaction for the dissociation of the weak acid, acetic acid. Now, we know that HCl is a strong acid, so it will dissociate completely. Right? So when 0.1 molar HCl will dissociate, I will get 0.1 molar H plus and 0.1 molar Cl minus.
That's right.
So that is irrespective of whatever else is present in the reaction, right? So 0.1 molar of H plus will come from HCl. The rest I'll start with 0.1 molar CH3CO minus, and suppose alpha is the dissociation constant, then alpha moles of acetate ion and alpha moles of H plus will be formed, but 0.1 molar H plus is already present, right?
Exactly.
So and obviously alpha, since CH3COH is a weak acid, alpha will be much less than 0.1.
That's right.
Okay. Now Ka, the acid dissociation constant, is given to me as 1.74 into 10 raised power minus 5, and the expression for Ka is CH3COO minus into H plus concentration upon concentration of CH3COH. Also, we talk about Ka only for weak acids, because strong acids dissociate completely.
Exactly.
Here, the concentration of CH3CO, okay, the concentration of H plus I can write approximate as 0.1, because alpha is much less than 0.1. So alpha plus 0.1 is approximately 0.1 into the concentration of CH3COO minus ions upon 0.1. 0.1, why? Because again, alpha is very small compared to 0.1. Right. So we say that 0.1 minus alpha is approximately equal to 0.1.
It's just time saving.
Yeah. So, and this is 1.74 into 10 raised power minus 5. So I will get the concentration of CH3COO minus as 1.74 into 10 raised power minus 5. Okay. So in the question, now a very important concept comes here called the common ion effect. According to the common ion effect, in a weak electrolyte, if let's say some ion is present, a common ion is present, like here CH3COOH dissociated into CH3CO minus and H plus, but common ion H plus was already present. In that scenario, the degree of dissociation of the weak acid decreases, as we can see that. In the first case, I will highlight this. In the first case, the CH3COO minus concentration was 1.32 into 10 raised power minus 3. But when a common ion is present, look at the amount of decrease in the acetate ion concentration.
That's right.
That is because of the presence of common ion H plus from a stronger acid HCl.
Exactly.
So yeah, this is another very important concept in ionic chemistry, ionic equilibrium.
So basically in this question we saw the common ion effect, which is very commonly found in questions, and secondly that the approximations for here, it was alpha less than 0.1. Such approximations are very commonly used because they just save time, and you'll see many such approximations coming forward in ionic equilibrium. And secondly, the common ion effect, we just need to, whenever any other acid, a stronger acid is present, it is applicable, and you just need to identify it and solve the question. So this was question number 12. So now we come to the 13th question, which says find the ionic product of water Kw and the acid dissociation constant Ka of water if the degree of dissociation of water is given to be alpha is equal to 1.8 into 10 to the power minus 9.
Yeah. So we know that water is a weak electrolyte, and this will be the reaction how the water will dissociate into hydronium and OH minus ions.
Right.
And it's a weak electrolyte, and we are given the degree of dissociation, which is 1.8 into 10 raised to the power minus 9. Right. So now we need to find the Ka and Kw of water. Let's say we start with a concentration of C, and initially these are 0. And let's say after some time, C minus C alpha amount of water is left, and C alpha moles of hydronium and OH minus ions are formed. Now, Ka of water as an acid will be given by this expression H3O plus into OH minus upon H2O.
That's right.
I can substitute the values C alpha into C alpha upon C into 1 minus alpha.
Right.
And I know that alpha, since it's a weak electrolyte, alpha is much less than 1. So I can approximate 1 minus alpha as 1. So Ka is nothing but C alpha square.
That's right.
Now we know the value of alpha, we need to find out the value of C. This is at standard conditions, 298 Kelvin. C is given by density upon molecular weight of water. Density under room temperature is 1000 and molecular weight is 18.
Right.
So the concentration is 55.55
molar.
I can substitute these two values in this equation, and I will get 55.55 into 1.8 into 10 raised to the power minus 9 whole square.
That's right.
So the value of Ka which we obtain is 1.8 into 10 raised to the power minus 16. Now we come to the next part. We need to find the ionic product of water Kw. It is given by hydronium ion concentration into OH minus ion concentration.
That's right.
So we can simply substitute the values. The concentrations are C alpha each. So Kw is C square alpha square. I can substitute the values 55.55 square into 1.8 into 10 raised to the power minus 9 whole square, which is 1.0 into 10 raised to the power minus 14. Now this is a very important point that we should remember. The value of ionic product of water is 1.0 into 10 raised to the power minus 14 at 298 Kelvin, that is 25 degrees Celsius at room temperature. This result must be remembered.
Exactly. So this was question number 13, and here we see that it's very important to remember. We could just memorize the result of this as a whole, and secondly that this is at temperature of 25 degrees Celsius. And thirdly, we should pay concentration on when we can use the approximation Ka is equal to C alpha square, because it is not valid at all times. So we must be very careful with the Oswald dilutions law, and that's what was used in the question, and its answer could actually be memorized as a result. So this was question number 13. So here comes question number 14, and it says H2S plus H2O is in equilibrium with H3O positive plus HS minus, and the Ka1 for this reaction is 1.1 into 10 to the power minus 7. And secondly, HS minus plus H2O gives H3O positive plus S2 minus, and Ka2 for the reaction is 1 into 10 to the power minus 14. And we are given that the concentration of H2S is 0.1 molar, and we have to find number 1 the concentration of H3O positive ions, and secondly the concentration of sulfide ions. So how will we proceed with this question?
Yeah, so this is an example of a dibasic acid. A dibasic acid can release two H plus ions in aqueous solution. But here we see that the Ka1 of the acid is much greater than the Ka2 of the acid. So the dissociation of HS minus to release H plus can be neglected when you compare the hydronium ion concentration from the first reaction. It will be much higher than that from the second reaction.
Exactly.
So ionization at the second stage is neglected. Okay, so for the first case, when I need to find the H plus ion concentration, I can consider H2S as a weak monobasic acid.
Monobasic meaning its basicity is 1. That
Basicity is
is,
one.
it can give, that is, it has one furnishable H plus ion.
Yeah. We're doing this because the hydronium ions obtained from the second reaction will be negligible as compared to the first one. So since it's a weak electrolyte, since Ka1 is small itself, I can use Oswald's dilution law again. This is a concept which is going to occur very often in ionic equilibrium, so you should be thorough with it. So the hydronium ion concentration by Oswald's dilution law will be given by under root of Ka1 into C, which is under root of 1.1 into 10 raised to the power minus 7 into C. It's given to me as 0.1.
That's right.
So I get 1.05 into 10 raised to the power minus 4 molar.
Right.
Now we come to the second part of the question, where we need to calculate the concentration of S2 minus ions. Now, for calculating the concentration of S2 minus ions, I need to take into account the second reaction. The second reaction, where HS minus dissociates to release H3O plus and S2 minus, is given by this. The Ka2 is 1 into 10 raised to the power minus 14.
That's
Okay.
right.
So I can write the expression for Ka2, which will be H3O plus into S2 minus upon concentration of HS minus. Now, this I know is 1.0 into 10 raised to the power minus 14.
Right.
Now, the hydronium ion concentration we calculated in the last step, the last part, is 1.05 into 10 raised to the power minus 4, because that will be the dominant, as in the amount of hydronium ions from the first reaction will dominate.
Exactly.
So they will, it will be equal. These approximations, once with practice, they'll come naturally to you. The concentration of S2 minus ions I need to find out. The concentration of HS minus ions can be taken as 1.05 into 10 raised to the power minus 4, because the ionization of HS minus is very small. So from the first reaction, we can see that the concentration of H3O plus and concentration of HS minus are both same,
Exactly.
equal to 1.05 into 10 raised to the power minus 4. So yeah, I can write this over here. I'm sorry, that is 4 minus 4.
Right.
And I know the value of Ka2, which is 1.0 into 10 raised to the power minus 14. These two values will cancel, and I will obtain the concentration of S2 minus ions as
10 to the power minus 14.
10 raised to the power minus 14
That's right. So basically, we saw that it was not a very difficult question, but again, we need to be very thorough with the Oswald's dilution law, and we obviously know that Ka1 is greater than Ka2, and we should be able to make a check where this approximation of C alpha square is equal to Ka is valid, and just do the question. So this was question number 14. So we come to question number 15, and it says the salts NaX, NaY and NaZ, that is 3 sodium salts with concentrations of 0.1 molar each, have a pH of 7, 9 and 11 respectively. Now we are supposed to arrange these acids HX, HY and HZ in increasing order of their acidic strength. Also we have to find the dissociation constant Ka wherever possible. So how will we do this question?
Yeah. So here we're given 3 salts, NaX, NaY and NaZ. Okay, and the concentration is 0.1 molar each. The pH is given as 7, 9 and 11. Okay, we need to arrange the acids HX, HY and HZ in the right order of their acidic strength. We'll consider the first case of NaX. Okay, these salts are sodium salts. So the base involved is NaOH, sodium hydroxide, which is a strong base. We just need to analyze the acids. So for NaX, the pH is given as 7. The salt is neutral, and we know that the salts of strong acids and strong bases are neutral in nature. So we can conclude that HX is a strong acid.
That's right.
Now we come to the second salt, which is NaY. The pH is given as 9. Since pH is greater than 7, the salt is basic.
Right.
So salt hydrolysis takes place and the solution is basic, right? Which means that since the base is a strong base, the acid has to be weaker. So HY is a weak acid, since the solution is basic. And we know the formula for the pH of a salt with a strong base, salt of a strong base and a weak acid. It is pH is equals to 7 plus pKa by 2 plus log of C by 2, which is 9, given to me in the question.
Right.
I can simply substitute the values and find pKa. Log of 0.1 by 2 is 9. So pKa I will get as minus, I'm really sorry, it is 5. So Ka will be 10 raised to the power minus 5.
That's right.
And similarly for the third case, the pH is greater than 7. So the salt, it's the case of a salt of a strong base with a weak acid. So I can use the same formula.
Exactly.
If I do the similar calculations, I will obtain pKa as 9, and therefore Ka is 10 raised to the power minus 9. Now I need to arrange the acids HX, HY and HZ in the order of the acidic strength. HX is a strong acid, HY has a Ka of 10 raised to the power minus 5, and HZ has a Ka
10
of
to the
10
power
raised to the power
minus
minus
9.
9. So HX is definitely the strongest acid. HY, the dissociation constant Ka for HY is greater than that for HZ. So HY is a stronger acid than HZ but a weaker acid than HX, and HZ is the weakest acid. So this is the right order.
That's right. So basically this was not a very difficult question, and you get many such questions in JEE asking about acidic and asking to compare acidic and basic strengths, and these are not really difficult to solve. Once you get in practice, you could just solve them shortly and save time. So this was question number 15.